All right. So, lesson 4 problems. I'm going to work with some common forces here. Um, Number 1, how much tension must a rope withstand if it is used to accelerate 1,200 kilogram car vertically upwards of this much meters per second squared, right? Ignoring friction. So, you know, it's best to draw a force diagram. So assume a spherical car, right? So here is my car. Now there are two forces acting on this car vertically, right? First will be obvious force, which is the weight of this car, Fg, okay? Fg. And the second force would be the tension of the rope pulling this thing up. Now, if the force tension is less than this Fg, this thing's going to accelerate down. But since it is moving vertically upwards with this much acceleration, your force tension better be bigger than your Fg, right? And I'm going to consider the direction up to be positive because that's the direction of motion. And that's very important to indicate this every time you solve a problem, all right? Now that we have this, now we can actually work with sum of all forces, I guess in the y direction. There's only one direction this motion is happening, right? I like to put the y down just to show that we're working in the y direction, is equal to MAY. This right here is acceleration in the y direction, okay? And sum of all forces in y direction is equal to, right? There are two forces, that is force tension, right, plus Fg. Now notice I put everything in vector notation, so this plus really means you're adding a vector. Now since Fg is pointing downwards, when we give direction to this Fg, it will be negative Fg, okay? So if we set these equal to each other, right, MAY, and since, right, is equal to, force tension looks like positive, and Fg is pointing in the negative. So I'm adding my negative Fg. That's what it really is, okay? So I can actually now start plugging and chugging, right? Because here, well, let's solve for F tension then, okay? Because this is just mg. Since this is negative mg, if I bring this negative mg to the other side of the equal sign, it becomes positive mg. So my force tension is equal to, right, MAY plus mg. Okay, I hope everybody sees that. If you don't see how I got to this, we can talk after class. So force tension is equal to mass of my car, which is 1,200. So this is the mass, right? Times the acceleration, which is 0.80, right? Plus 1,200 times 9.8. All right. So now if we take our calculators, say 1,200 times 0.8, and I get something like 960 for this one, right? Plus 1,200 times 9.8, and I get 11,760, right? So if I add 960 to the answer, my force tension becomes 12,720 newtons as my force tension. So notice my force tension is definitely bigger than my weight of the car, FG. Okay? All right. Any questions? All right, then let's take a look at number 2. I have a 10-kilogram bucket and it is being lowered by a rope in which there is 63 newtons of tension. Now you got to be careful with this, right? Which way do you want to call positive and which way do you want to call negative is very important. So here, assume my spherical bucket here, and this mass of this bucket is 10 kilograms. Right? And I have Fg, right? Fg of this bucket going straight down. Right? Now Fg, you know it is mg, m times g, right? You could also write that up there if you want to. Right? And tension is up. So if you think about it, Fg happens to be 98 newtons, right? But tension is only 63 newtons, pointing up. So F tension is equal to 63 newtons. Okay? Now, the direction of motion happens to be downward direction, and then acceleration is down this way, and I'm going to call the down direction positive, which means my tension is going to be negative and my Fg is going to be positive in this case. Okay, so keep that in mind. So we're looking for acceleration. Okay, we're looking for acceleration. So how do we start? We start with this. We start with sum of all forces in y is equal to m a y. And we're looking for the a y. Then sum of all forces in y is equal to, again, I have force tension and I have Fg, right? Now, don't forget, I'm going to make the direction of motion to be positive here. So I'm going to say my downward direction is positive. So if I set them equal to each other, MAY is equal to, my F tension in this case is negative, and my FG in our case is positive. Okay? So we know what Fg is. Fg is equal to 10 times 9.8, and that is 98 newtons. So here, my mass is 10 kilograms. AY is what we're looking for, is equal to negative 63 plus 98. So if I solve for acceleration here, right, acceleration in the y direction is equal to, well, what's 98 minus 63? That looks like 35, right? So that looks like 35 divided by mass of 10 kilograms, right? Therefore, my acceleration happens to be 3.5 meters per second squared. Okay? All right. Let's take a look at number 3. An elevator, mass of 4,850 kilogram is to be designed so that maximum acceleration is 0.0600 Gs. Now remember, 1 G is equal to, right, 9.8 meters per second squared. So this is really our acceleration, okay? That's our acceleration, which is 0.0600 Gs. However, right, 1 G, right, 1 G is equal to 9.8 . So 1 G is equal to 9.8 meters per second squared. Sorry, I ran out of room. All right. So let's find out what acceleration is in meters per second squared. So 0.06 Gs times 9.8. So notice how these G's will cancel out nicely, giving me meters per second squared. Right. So my acceleration comes out to 0.588 meters per second squared is what we have for acceleration. And this is good to know, okay? Now, when things are accelerating upwards, notice how the tension becomes greater than my Fg, right? When things are accelerating downwards, my tension is definitely less than my Fg. So we don't have to worry about when things are accelerating down. We have to worry about things accelerating up. Only when things are accelerating upwards, the tension has to be greater than the Fg. Therefore, if the tension can only withstand the weight of the elevator, that means it's going to snap when it's accelerating upwards. Therefore, we have to calculate the minimum tension required to make this elevator accelerate at that much. Okay? So, minimum force, we can worry about that afterwards. Let's talk about the maximum force. So we're going to talk about maximum force here first. Okay? And then we'll talk about minimum force afterwards. Okay? So again, if we were to take a look at where here's my elevator, okay, and this is accelerating upwards now. So here's my F tension, and here is my Fg. Right? And the acceleration is upwards, and that's the positive direction. Okay? Therefore, if we were to work this thing out, okay, it's again, you have to start with these two. Whether it's going up or down, these two lines were always identical, right? So sum of all forces is equal to MA, and then since it's in the y direction, we could keep it as MAY, right? And then sum of all forces in the y direction is equal to F tension plus Fg. Then, if you set them equal to each other, MAY is equal to, right, F tension, I'm going to keep that as positive because that's the direction of motion, minus Fg. So what is Fg? Right? Fg is, right, mg, and that is 4,850 times 9.8. So that looks like 47,530, right? So 47,530 newtons is my FG, right? Well, that value is not going to change whether it's going up or down, okay? So here, the mass of my elevator is 4,850. Acceleration is 0.588 meters per second squared. I know my FG, so I can solve for my F tension. Right? So F tension now is equal to, here, I got MA plus FG. So my force tension is equal to mass, which is 4850 times A, 0.588 times plus 47,530. So my force tension here, is equal to, okay, let's see what it is. 4850 times 0.588, and this becomes 2,851.8, okay, plus 47,530. So if I add 47,530, and I'll get my force tension is equal to 50,381.8 newtons. So this is on the way up. That's the maximum amount of tension required, or I'm sorry, minimum amount of tension required in order for this cable for not to snap. Okay? Well, now let's think about the minimum part. Okay? So here, sum of all forces in Y is equal to MAY. And then sum of all forces in Y, okay, is equal to, again, F tension plus FG. But this time, what's happening? Well, you know, this time we have elevator and FG is going down, right? FG is going down, and F tension is actually going up, and it's smaller, right? And downward direction is positive. Okay? So when we set this equal to each other, so MAY is equal to negative F tension, right, plus FG. So if I solve for F tension by bringing this to the other side, I get positive F tension now is equal to, right, MAY plus FG. I mean, negative MAY. Negative MAY plus FG. So my force tension is equal to negative, it's the same value as this, right? 2,851.8 plus 47,530. All right? So 47,530 minus 2,851.8. So my force tension now on the way down is equal to only 44,678.2 newtons. So notice it is definitely less than the weight of the elevator on the way down when it's accelerating down. All right? Any questions? All right, good. Good. All right. Number 4 is a good problem. A person stands on a bathroom scale, right, in a motionless elevator. When the elevator begins to move, the scale briefly reads only 0.75 of person's regular weight. Calculate the acceleration of the elevator, right, and find the direction of acceleration. Well, first of all, when you're standing on the bathroom scale of the elevator, your bathroom scale is actually measuring your normal force. Okay? So if somebody's pushing down on this person, then the bathroom scale would read more than the person's weight. If somebody's giving a little lift, the bathroom scale would read less than the person's weight. Remember, when tension is greater when elevator was accelerating upwards, right? And tension's less when accelerating downwards. So let's take a look at a free body diagram of this scenario. Okay? So here is a person standing on a bathroom scale. That's a rather large scale. Okay? Let's draw, right, force diagram, right, acting on this person. So we're not going to worry about the tension, okay, and the mass of the elevator. We're just worried about this person on the bathroom scale in the elevator. So here's the FG of the person. Then, what's supporting that person? That support force is the normal force, F normal, by this on the person by the scale. Okay? This is what the bathroom scale reads. Okay? And we don't even know the mass of the person. But I know the weight of the person is equal to mg. But this normal force happens to be only, right, 0.75 of mg. Okay? Now, let's think about this. Are we going to assume going up is positive and then going down is negative? We don't know whether this thing is going up or down, right? So we're going to have to assume something. So if we assume that this person is accelerating up, we're going to call up positive. Or if we're going to assume that this person is accelerating down, we're going to call down positive. But we don't know. But if we assume up to be positive, and if our answer comes out to be negative acceleration, that means the acceleration is going down. Okay? However, if we assume that this person is accelerating downwards and the answer comes out to be positive, that means we correctly assume the right direction. All right? So just for the argument's sake, I'm going to assume wrongly and say, oh, I'm going to say this person is accelerating upwards, and I'm going to call that positive. And let's see how that works out. All right? So now we can say sum of all forces in y direction is equal to m-a-y. And sum of all forces in the y direction is equal to, we have F normal, and we have Fg. So if we set them equal to each other, MAY is equal to F normal. I'm going to call that positive in this case, right? So positive F normal minus Fg. So plus negative Fg. So we don't know the mass, so we're going to just keep it as that. Okay? And that is equal to, my F normal happens to be 0.75 times mg minus mg. Well, here, if I add these two together, this looks like negative 0.25 mg. And that is equal to my MAY. Ooh, look what happens to my mass. It cancels out. So my acceleration in the y direction happens to be negative. So this elevator is going down or accelerating downwards. Okay? It's accelerating downwards. It doesn't necessarily mean the elevator is going down direction, because it could actually be going up and slowing down, and that means acceleration is also in the downward direction. So we really don't know the direction of motion, actually. So right now, all we know is the acceleration is downward direction. That's all we know. All right? So here, this looks like negative 0.25 times 9.8. So what is my acceleration? My acceleration in the y direction is equal to, right, negative 2.45 meters per second squared. And since we assume the up direction to be positive, the acceleration then is in downward direction. Okay? Downward direction. So notice how mass is independent. Okay? Now let's do this again with in the opposite direction to be positive. Let's see how that works out. Sometimes you pick the wrong direction, and sometimes it works out, and sometimes you pick the positive direction and still works out. So let's take a look what happens when we have, this time we have person standing on a scale inside the elevator, but we're going to assume down to be positive. All right. So here, in this case, we have Fg again, which is equal to mg. And the normal force is going to be from the floor of the, well, not the floor, but the scale, right? From the top of the scale to the person's feet, right? Which happens to be, right, 0.75 mg. Okay? So if we were to do this, sum of all forces is equal to MAY. And then sum of all forces is equal to, again, F normal plus Fg. So MAY is equal to, this time my F normal is negative. Right? And my Fg happens to be positive. So MAY is equal to negative, right, negative 0.75 mg plus mg. This is 1 mg, right? So look what happens. MAY is equal to positive 0.25 mg. And since masses cancel out again, my AY becomes positive 2.45 meters per second squared. And that makes sense. Look, it's still down because it's positive, and we call positive down. It's still, acceleration is acting downwards. Right? So whether you guessed correctly or incorrectly, you should still be able to interpret correctly. All right? So just because you got negative, you don't panic. You just have to know how to analyze what you got. All right? Any questions? All right. Very good. Very good. Now let's take a look at number 5. Okay. All right. A box weighing 70 newtons rests on a table. A rope tied to the box runs vertically upward over a pulley, and the weight is hung from the other end. Determine the force that the table exerts on the box if the weight hanging on the other side of this pulley weighs A, 30 newtons, B, 60 newtons, C, 90 newtons. All right? So A, I'm going to do it in purple. B, I'm going to do it in aquamarine blue. And C, I shall do it in forest green. Right? So, what would happen if I had 30 newtons of force hanging on this thing. This would actually create a tension on this string to be 30 newtons. So the 30 newtons of tension will be pulling this box up, where Fg only happens to be 70 newtons. All right, so let's take a look at A. If I were to do a force diagram for A, right, my Fg would be that. And that will be always 70 newtons. Then I have a normal force going up, like so. And I would have tension, F tension of 30 newtons pulling it up. Okay? So it's kind of obvious though, right? This plus this plus this has to be 0, because I don't think this 30 newtons is good enough or big enough to lift this 70 newtons off the table. All right? So we can say simply sum of all forces, right? Sum of all forces in the y is equal to MAY, right? And then sum of all forces is equal to, right? I have, right, F tension plus F normal. Oh, I should have used different color. Crap. All right, we'll work that out, guys. Sorry, we'll work that out. Maybe I'll use red in here instead. Red, I'll use red. All right, so here, if I say MAY, again, I'm going to consider direction up positive. That doesn't really matter again, because it's not going to be moving, is equal to, right? Oh, I forgot the FG, sorry. So tension looks like positive. F normal looks like positive. Fg looks like negative. My acceleration of this is not going to happen. My acceleration is 0 for that, right? 0, because this is not big enough to lift this thing. So 0 is equal to then, right, 30 plus F normal minus 70, right? So my F normal in our case is equal to, I bring this to the other side, becomes positive 70. Right? I bring this to the other side, it becomes negative 30. So my F normal in this case is equal to 40 newtons. For part B, again, if the tension now is 60 newtons instead of 30, it's not going to still lift up. So my acceleration is going to be 0, right? So sum of all forces is equal to MA, the y direction, and then sum of all forces is equal to, this time I have F tension, which is 60 newtons, plus F normal, right, plus Fg, right? Again, MAY is equal to, again, this goes to 0, force tension, which is 60, F normal is what we're looking for, and it's positive, minus 70 So my F normal happens to be just 10 newtons of force for part B. Now for part C.
Mr. Kim,
Yeah.
shouldn't the FG be 60 for part B?
No, the weight will never change.
Oh, I see where you got that. Never mind.
Yeah, it's the normal force. This is basically this hanging mass right here. This will create a tension of 60 going up. Does that make sense?
Yeah, I was just confused for a
Yeah.
second. Thank you.
All right. Now for part C. Now for part C, right? I'm going to hang 90 newtons of force here. And this thing is only 70 newtons. So what's going to happen? Will this get lifted? Come on, it's yes or no.
Yes.
Thank you. Thank you, Sean. All right. So we're going to have acceleration here. We're going to definitely have acceleration here. So since it's going to be lifted, do I even have to calculate it? The normal force is going to be then what? What do you think? If this thing is lifted off the floor, how much does the table have to support this box? Good, like you said, nothing, zero. Very good. You guys, yeah, nothing, zero. So there's going to be acceleration happening. So my F normal for part C goes to zero because this thing will be off the table. There will be no F normal. It's very important to understand that. Okay? Now, that does not mean tension's going to be 20 newtons. We're going to calculate this later because I don't have enough room. It's going to take about half a page. In this case, because this thing is rising up and this thing is lowering down, there's going to be acceleration of the whole system. And the tension will not be 20 newtons, it'll be something else. Okay? All right. Sarah, you have a question?
When do you know when to multiply like the weight by 9.8 for the FG?
You don't multiply weight by 9.8. You multiply mass by 9.8 to get the weight. The mass is measured in kilograms. So don't get confused between mass and weight. Here they give us weight of 70 newtons, right? But if they were to give this to us as like 10 kilograms, then in order to get the weight, you have to multiply that 10 kilograms by 9.8. But here they already gave us the weight at 70 newtons. So we just use weight at 70 newtons. Is that good?
Yeah.
All right. It's a very important question that you asked, and that's good. I'm glad you asked that because other people are probably confused too. So when they give it to you in newtons, don't multiply it by 9.8. Matter of fact, in order to find the mass of this thing, or this thing, you have to divide this 30 newtons by 9.8 to get the mass. All right. So for part C, I'm not going to worry about it because my normal force is, right, 0. All right. Number 6. Draw the free body diagram for a basketball player just before leaving the ground on a jump and while up in the air. Okay? Well, all right, so here's my b-ball player right here, right? Colin Gillespie, right? Who's a doppelganger is Archdiakono, right? So here is a basketball player holding somebody's head, all right? All right, never mind. That's kind of all right. Basketball, right? Let's take a look at forces acting on this person. Right? Well, obvious force is the Fg straight down, right? Okay. Normal force from the floor straight up. Right? Since he's not accelerating, the net force is 0, so F normal plus Fg has to equal to 0. Now F normal positive, Fg negative, so F normal in this case is equal to Fg. However, when he jumps, right, he's no longer supported by, right, he's no longer supported by the floor. He doesn't need to be supported by the floor. So only force he has is just gravity. That's it. Gravity is the only thing acting on the person when it's up in the air. Okay? No normal force. All right. 7. Sketch the free body diagram of a baseball at the moment it is hit by the bat, and again after it has left the bat and is flying towards the outfield. All right, so we have two scenarios here. So here's a scenario 1, and here's a scenario 2. So for part A, here's the baseball. Right? And the bat. And the bat is like, I guess you could think of bat. It's like here, right? It's like, so you can. The bat hits the baseball. Well, the obvious force is going to always be Fg, right? Fg will always act straight down. Fg. Then you will have the normal force on the ball by the bat going this way, right? Force normal on the ball by the bat, okay? It's a force applied. Force of bat, okay? This is actually the normal force on the ball by the bat, okay? That is on ball by bat. Then you have force normal on bat by ball. All right. After the ball flies off, only force that is acting on the ball, if we can neglect the air resistance can do wonders on the ball. However, if we were to neglect any air resistance, only force on the ball after it flies out towards the right field is just FG. Just FG. Because remember the projectile motion? This FG is what's causing the acceleration in the y direction. And that is 9.8 meters per second squared. That's it. No other forces. Okay? All right. All right. Yeah, maybe I should call this F normal instead of F bat. F normal on ball by bat versus F normal on bat by ball. Okay? So F normal. All right. Number 8. Two forces, F1 and F2, shown here in figure 4-39A and B. This is like looking downwards. Okay, this is a bird's eye view. Act on 27 kilogram object on a frictionless tabletop. Okay. Find the net force of an object and its acceleration for each situation. I think we did a similar problem like this for example problem. Okay. I don't know if you remember it, but we did. So you better know how to do that problem because you're going to be asked again, most likely. All right. So please, if I could find it, I'll show it to you. And voila, here it is. Okay. It's on page 17, right? It's on page 17. So you should be able to do this no problem. So F1 happens to be 10.2 newtons. Right, so F1 is 10.2 newtons. And F2 happens to be 16.0 newtons. So this is for A, right? So let's take a look at what happens if we could find F1 as Cartesian form. So it's negative 10.2 x hat plus 0 y hat newtons for my F1, right? And F2 happens to be 0 x hat negative 16.0 y hat newtons. So the net force happens to be right, negative 10.2 x hat minus 16.0 y hat newtons. Okay? Therefore, the magnitude of my net force is equal to, right, square root of 10.2 squared plus 16.0 squared. And that comes out to, right, plus 16 square root it. I get something like 18.97, right? Or simply 19 meters, 19 newtons, right? 19 newtons. Therefore, since, right, my acceleration of this happens to be which is 18.97 over mass, which is 27.0 kilograms. So if I divide that 18.97 by 27, I get acceleration of 0.703 meters per second squared. But that's not complete. Why? Because this will have direction. Must have direction, actually. All right? This must have direction, this net force. Okay? So how do I find this angle right here? This angle here is beta. And this angle here happens to be my theta. Okay? So you can find beta is equal to tan inverse of, right, negative 16.0 over negative 10.2. So what is the beta? Beta is tan inverse of 16 divided by, then I get 57.5 degrees. Therefore, theta is equal to 180 plus that, right? 180 plus beta, and that is 237.5 degrees as my angle. So you must have both of these. Okay? You must have both of these. All right. So that was easy. Okay, that was easy. So now let's take a look at the second one. Okay. The second one, your F1 in Cartesian form, this angle here happens to be negative 30 degrees. All right, or simply this theta 1 happens to be 330. All right, so theta 1 is equal to 330 degrees. So let's find the components of this, of F1, right? So F1x is this way, and F1y is this way. So F1x is equal to F1, which is 10.2 times cosine of 330. And that comes out to 8.83 newtons x hat. And F1y is 10.2 sine of 330. And that comes out to, right, negative 5.1 newtons y hat. So we can just add them up again. So here my F1 is equal to, right, 8.83 x hat minus 5.1 y hat newtons. And F2 is easy, right, because it's on the axis. F2 is 0 x hat, right, plus 16 y hat newtons. All right. Therefore, sum of all forces comes out to 8.83 x hat, right, plus 10.9 y hat newtons. Then we can figure out the magnitude of my net force. Right? The magnitude of my net force. So this thing's gonna go like this way, I guess, somewhere like this is my net force. 10, yeah. So I don't know. It's gonna go like something like that. Okay, that's my net force. So square root of 8.83 squared plus 10.9 squared. Square root that, and I get 14.03 newtons. Right. Now this angle here, theta, so theta is equal to just simply tan inverse of 10.9 over 8.83 because it's in first quadrant. So tan inverse of 10.9 divided by 8.83, and I get 51 degrees. Okay? So acceleration is equal to the net force divided by mass. Therefore, 14.03 divided by 27. So my acceleration comes out to 0.52 meters per second squared. That's my acceleration. And the direction stays the same, which is 51.0 degrees. Whew. All right. Any questions so far? All right. So, what time is period over? 52? All right, good. We're doing good in time. All right, then. Let's take a look at the next page. If the acceleration of a body is 0, are no forces acting on it? Now, these are very good conceptual questions for multiple choice questions, right? So it's probably a good idea to memorize these or make sure you understand them. All right, so if the acceleration of a body is 0, are no forces acting on it? If the acceleration of body is 0, right? Then the net force is 0. But other forces. There could be other forces, right? That could add up to 0. So, no, there are forces acting on it, obviously. There has to be more than one. Minimum of 2, right? All right. Or it could be no forces acting on it. But that doesn't always mean there's no forces. There could be 2 forces acting on it. It just means the net force is 0. All right, then, let's take a look at number 2. Why is stopping distance of a truck much shorter than for a train going at the same speed? Well, distance for the truck, right? If the same amount of braking power is applied, right? So mass of the truck, they're both T's, huh? I guess truck, and then mass of the train, right? And mass of the train is definitely much bigger than mass of the truck. Okay? If they're going at the same speed, okay, initially, the acceleration of the train or the deceleration of the train is probably going to be a lot less, because if you were to apply the same amount of brake force, right? So the acceleration is equal to the force brake divided by mass of the train, right? Train, I forgot the R, right? Is very small. Right? But the acceleration of the same force, brake force, divided by the mass of the truck, right, is bigger than train, right? So this will come to a stop much faster than the train. Matter of fact, this will probably come to a stop in like 300 yards, but this thing will come to a stop in several miles. Okay, that's why you should not be playing on the train tracks, because it takes forever to stop that train. Can coefficient of friction exceed 1? Yes, actually, in lab situations. Okay. For static, coefficient of friction can be greater than 1 in some cases, especially the static one. Okay. Since mu is equal to F friction divided by F normal, it can be produced in the lab situations. All right. So a heavy crate rests on a bed of flatbed truck. When the truck accelerates, the crate remains where it is on the truck, so it too accelerates. What force is causing the crate to accelerate? That's a great question. So here we have a truck, right? And this truck is carrying a crate, right? Now, if this truck flatbed did not have any friction, it's like, no friction at all. When truck leaves, when it accelerates, this crate's going to remain where it is, and it's just going to fall off, right? But if the truck is accelerating and crate stays with the truck, what's going to be needed in order for this crate not to slide off the flatbed of the truck? It's going to have to be friction. And friction has to act in the direction of motion of the truck. And this is a accelerated frame of reference, which is non-inertial frame of reference. So this case, when things are accelerating and you are in the accelerated frame of reference, you will have friction making things accelerate. Okay? So friction is keeping the crate, right, from sliding off of the flatbed, okay, which will make the crate stay on the truck. It's the friction. All right. And last question. Last question is, can you hold a heavy box against a rough wall to prevent it from slipping down by pressing only horizontally? Okay. How can application of horizontal force keep an object from moving vertically? So here's the wall. This is the wall. And we have a box. Okay. Heavy box. Well, if I were to apply force onto this box, so if I push up against this box, so F push against this box, because I'm pushing up against this box, this will create a normal force back onto the box by the wall. F normal on box by wall. And these two forces are equal to each other. And because the normal force is acting on this box against the rough wall, it would create a friction up this way to preventing it from sliding. That will be, hopefully, be equal to or greater than the Fg. So as long as this normal force creates enough friction caused by the wall and the box, which is mu sub s, right? That's greater than or equal to this Fg. So if the frictional force, right, can be created by the normal force times mu sub s greater than or equal to Fg, then your frictional force will keep this box from sliding vertically. So it doesn't always have to be greater. This frictional force is always going to be equal to this Fg, but it can be calculated to be greater than the Fg because this friction is only going to be a reactive force. So by pushing up against the wall, creating normal force from the wall to the box will create friction, and mu sub s times friction, normal force will give you friction, And as long as this value is equal to or greater than FG, it would hold up there. All right. That's it for today. All right. Hope you got all this. I will again post this in PDF format on Schoology as well as this lecture video. So have a wonderful weekend. Please stay safe, everybody. I, I guess I'll see you from school on Monday or Tuesday, I guess, for you guys. But Thursday, I may not be able to come to school Thursday because I've got to take my son to the hospital. All right. Have a nice day, everybody.